All right. Success. You know why they say recording in progress, right? To make it Tony proof. If they don't say it, I won't know if it's recording or not. I'm not smart enough to see the little recording thing on the left-hand side. So you have to have redundant systems when Tony's operating things. All right, Rebecca, you were here first, so I'm going to let you have the first go. Do you have a question?
Yeah, it's more of a general question.
Okay.
When coming up with the net formula for a gas forming reaction,
Net ionic?
yeah, the net ionic, what
Sure.
are what are you supposed to put in it? I don't know. I think I had trouble finding that.
I'm going to do a change share here so that you can see my tabletop and my elbow. Okay, so here we go. Trying to get the paper aligned. Okay, so let's say that we want to write a net ionic equation for um, sodium carbonate. And sodium carbonate is also called washing soda. You can actually buy it in the supermarket. And let's say we mix that with hydrochloric acid. And hydrochloric acid, when you buy it, it's going to be the acid dissolved in water. So it's HCl. And when you do this reaction, this gas forming reaction is going to produce three things. One of them is H2O. One of them is CO2, and that's your gas. And the other is a salt. And the salt is going to form some sodium and chlorine. And so you'll have sodium chloride, and that will be dissolved because anything with sodium ions is soluble. So this is the reaction. It's not balanced, but I'm going to go ahead and balance it. You see we have two sodiums here and one here.
Yeah.
We have one hydrogen here and two here. And now we have two chlorines and two chlorines, one carbon, three oxygens, 1, 2, 3 oxygens. Okay?
Mm-hmm.
Okay, so to write your net ionic equation, anything that is not aqueous is going to be in your net, exactly as it's written. So here, this sodium carbonate, while it is water soluble, we started off with this S, so it was not dissolved. So I'm going to say this one more time. Anything that is not aqueous, you bring right down into your net. So are we okay so far?
Yeah.
The next thing you do is you take a look at what remains and you ask yourself, if this is aqueous, what is the formula? So for HCl, because it's a strong acid, it's H plus and Cl minus aqueous. And naturally, since I have this 2 here, I actually have 2 of these and 2 of these. So this is what 2HCl represents when we write aqueous, because it is a strong acid. So what does this represent over here, the 2NaCl aqueous? Well, it represents 2 sodium ions that are aqueous and 2 chloride ions that are aqueous. So when we write these out here, what do you do with them? Well, if there's anything that is identical, it doesn't belong in your net ionic, because the net ionic is only for those things that change, not for those things that do not change. These things that do not change are called spectator ions. And so these 2 H's, H pluses, I should say, belong in your net. And when we put them in here, you can see that this is balanced. Oh, actually, you can't see that it's balanced. I forgot the 2 sodiums. Okay, so now we have everything in the net that we should have. So do you see we have 2 sodiums and 2 sodiums, 1 carbonate, or 1 carbon, 1 carbon, 3 oxygens, 3 oxygens, 2 hydrogens, 2 hydrogens. So this would be your net. Any questions about that?
So first you look for what makes the carbonate and
No. First, I look for all solids, all liquids, all gases, and they go in the net.
for the net, yeah.
Yeah, so here's a solid.
But for these reactions, it's like a carbonate creating water and CO2.
Well, this is the most common gas forming is you have this CO3 combined with hydrogens. And the key to balancing these types of reactions is simply this. You need 2 H pluses and 1 CO3, and that actually forms carbonic acid. But this is very unstable. And what happens is one of these oxygens combines with hydrogen, and you get H2O and CO2. So this you never see, because once it's formed, it immediately goes away.
Okay, so you take
Kind of like a bacon sandwich around my house. Once it's made, it immediately disappears. Okay. So do you see how, if you focus on these 2 products, you need 2 hydrogens and 1 CO3?
Right.
Okay, so now let's take a look at another one that I'm going to make you do. So I'm going to change things a little bit. NaHCO3 aqueous plus HCl aqueous gives you CO2, H2O, and again, NaCl. So what would the net ionic reaction look like for this one?
Well, I'd want to put the
Which ones do we bring down automatically?
automatically the gas and the liquid.
Okay.
So CO2 and H2O. And I know that a CO2 and an H2O makes a CO3, so I'd be inclined to bring down the first species or
We
whatever.
don't want to do that. Whenever it says aqueous, you have to decide what does that form.
Oh, okay. So it would be Na plus, H plus, and CO3 2 minus.
No, it would form HCO3.
Oh, okay.
And the reason for that, and not H plus and CO3 2 minus, the reason not this, not that, is because this is a weak acid. And so when it's a weak acid, you keep it together.
Right. Because it doesn't fully ionize.
Right. In fact, it mostly doesn't ionize. It's like 100,000 to 1. So you really want to write the form that is most prevalent. So that's the form that this takes. What's the form that HCl takes?
H plus Cl minus.
Now, why do we separate those when that's also an acid like this?
Because hydrochloric acid is strong.
Correct. Okay, so what form will NaCl take?
Na plus Cl minus.
So what things are in common on both sides of this equation? It looks to me like through my chicken scratch, I can see that the chlorides are the same. The sodiums are the same. They're both aqueous, right?
Right.
Is it aqueous or aqueous?
I mean, I would say aqueous.
So is it Aquiman or Aquaman?
Aquaman.
So it's aqueous. There's an E. Aquaman. So it's aqueous, you're right. I'm just messing with you. All right, so do you see how H plus is not on both sides? So that's going to be in our equation, correct?
Right.
And HCO3 is not on both sides, so it's going to be in our equation. And if we've done this right, this should be balanced. How many hydrogens do we see on the left?
2.
And how many on the right?
2.
1 carbon on the left, 1 on the right, 3 oxygens on the left, and 2 here, and 1 here for 3 total. So the key to doing this, if you wanted to write out steps, would be number 1, start off with a balanced reaction, right? What would step 2 do? And this is for getting your net.
Bring the solids down into the net, or anything that's not aqueous, so a gas.
Bring solids, liquids, gases into the net. And then what's 3?
You want to make the charges of every element in the compound.
I would say it differently. I'd say determine the ions in the aqueous.
Okay, yeah.
And then 4 would be same aqueous ion on left and right. Do not make the cut. So what do I mean when they do not make the cut?
They cancel out.
They don't go in the net. So 5 would be the other aqueous ions are in the net. So step by step, isn't that pretty much what we did?
Yeah, exactly.
Okay. And this is something that, you know, when you're looking at examples of what is being done in lectures and stuff, a lot of times this is not done for you. I don't normally do this. I show you how to do it, but it helps to write out your own directions for what you just saw. The reason I don't write out these directions is because it's just something to memorize, and I'd rather kind of you have the concept. And if you look at the net ionic reaction concept here, we're basically only including those things where something has changed about them. That's the net. Here, sodium is part of a solid. Here it's dissolved. Something has changed. Here, this carbon is part of carbonate ion, and here it's part of CO2. Something's changed for that carbon. So the net is really for things that change. And here, this is a chloride ion, 2 of them, in fact. Here, these are 2 chloride ions. In both cases, they're aqueous. Nothing has changed, so they're not in the net.
Okay.
So the net is for things that have changed. The total reaction is for everything. Okay?
Yeah, thank you.
All right. Now you're up there, Charlotte.
I don't have any specific questions.
Okay. How about you, Jessica? Do you have any specific questions?
Nothing specific.
Okay, then we're going to get to doing some problems in the back of the book, which I always find helpful for students to examine. So we had gone through 2 through 26, I believe. So 24, we decided which of these were soluble based on the solubility guidelines. And here we had done 26, where we actually balanced this reaction, I believe, and came up with the correct S, L, AQ, and gas. And now we're going to take a look at these. So with these, we're looking at predict the products of each precipitation reaction. So in this case, we know it's a precipitation reaction. Okay, so precipitation reaction, and I'm going to write PPT RXN, where PPT stands for precipitation. I don't want to write that out. It's just too long. And reaction, I'm going to whittle it down to 3 letters, one of which is not even in the word reaction. But X does sound like it belongs in reaction, if you know what I mean. Okay. So for precipitation reaction, we basically have 2 aqueous ionic compounds mix and form a solid ionic compound. That's basically what we're doing here. And you can see my abbreviation for compound and my abbreviation for aqueous. So that's an aqueous reaction. So here, what I like to do is I like to write out the ions in solution. So here I'm going to have a lead 2 ion. And I'm not going to bother with aqueous because I know it's aqueous. It says so right there. So I'm not going to bother with that. I know that I have 2 nitrates. I know that I have a potassium. And I know I have a bromide. Now, if we look at our solubility guidelines, it tells you that these are soluble. And it tells you that these are soluble. So if they're soluble, they can't be in a solid that forms in solution. Because if that solid did form in solution, it would immediately dissolve. So guess what? It never forms. So if this is a precipitation reaction, it has to be between these two. And we have to think about, well, what would be the proper formula of a solid with these two? And the answer would be PbBr2. Remember this switch and simplify? So that's your solid. And so our answer for A would be Pb. I'm not going to write all of this down. I guess I should. NO3, 2 plus KBr makes PbBr2 solid. Now, what do you want to do? Well, you want to figure out what this other piece is. This other piece is going to be the 2 ions that are not going to meet together and form a solid. And because they're always soluble, that will be aqueous. And we just have to worry about balancing now. So if I put a 2 here and a 2 here, we'll see that I have 2 potassiums, 2 bromides, 2 bromides, 1 lead, 2 nitrates, 2 nitrates. So in trying to figure this out, what were my steps? Number 1.
Decide what's soluble.
Nope. Look at this. What did I do here?
Oh.
Step 1, get the ions. Once you get the ions, what decision do you make? Well, the always soluble ions are not the solid. The always soluble ions are not in the solid. And so 3, the leftovers must form the solid. You won't always have 2 ions that are always soluble. It might only be 1. And then you have to figure out what's going to work best. And then when the leftovers form the solid, what do? The solubles form an ionic compound that's aqueous. And then you balance. So you can see in these steps, they're broad steps. Like when I say the leftovers must form the solid, you'll notice I say, and make sure you get the right formula for the solid. That's kind of a given. And here, the soluble form an ionic compound, I don't write and. The formula's got to be this a formula of an ionic compound. That's kind of a given. So now we know what to do, right? It's easy as 1, 2, 3, 4, 5. So let's try that for B. What are the ions in calcium nitrate?
Calcium 2 plus, nitrate minus.
Right, and we don't even need to put a 2 here. We just need to know that that's one of the ions, really.
Okay.
And what are the ions in KF?
Uh,
K
K and F, that's it.
and F. Which one of these are always soluble?
Nitrate.
So I'm going to put sol underneath this one, sol underneath these. So they're not the solid. So if these two, because these are precipitation reactions, if these two form a solid, what does the form have to be?
CAF 2.
Correct. And if these two form the other thing, what does the formula have to be?
KNO3.
Right? And we put aqueous. And so now we can balance. And here, can you see how we have one calcium, two nitrates, one nitrate? So we're going to put a 2 there. One potassium, two potassium. So we put a 2 there and we're balanced. Now, what's the net going to look like? So what do we do when we make the net? First thing.
Everything that's not aqueous.
So in this case, there's only one thing. And then for this one, you know, it's pretty obvious that on this side, you're going to have calcium and you're going to have fluorine. What is the form of calcium over here? It's aqueous. And what is the form of these fluorides? They're aqueous. And so there's your net. From the above, we know this guy can't be in the net. We know this guy can't be in the net because they're always soluble. So I forgot to do the net for A. So why don't you do the net for A? Here's A. What's the net?
PB2 plus aqueous plus. Would you do 2Br or Br2?
It's 2 BRs because Br2 is a molecule.
Okay. So plus 2Br minus.
Yep. And it makes peanut butter and jelly sandwiches. Well, PBR2. Right?
Right.
So that's your net. Because we're bringing this down. Boom. And here we have 2 bromide ions. So that's that. And again, Br2 is a molecule that's neutral. 2 bromide ions have a -2 charge altogether, a -1 charge each. So they can't be the same thing. And my lead ion here is really horrible looking. So I'm going to cross this out and I'm going to put 2 plus right there. Okay, so I'm going to leave C to you guys. Well, actually, let's do a little bit on C just to get you started. So I think it's obvious what the ions are here because we just did that one above, right? Now here's a weird one. What are the ions? Well, we know for sure we have 2 sodium ions. And whenever you see a formula like this, you're going to assume that this only has 2 types of ions, a cation and an anion. So these are the cation, right? There's 2 of them. So if these are the cation, what does that mean about the rest of the formula? And the answer is it's an anion. If we had a parentheses around that, that would mean we had maybe 2 or 3 or 4, correct? There's no parentheses, so we only have one of them. What's the charge on that ion have to be?
2 minus.
2 minus. So now we know that the nitrate is always soluble. The sodiums are always soluble. So the solid must be between this calcium and this guy here. This is one of the ones that I don't have you memorize, but if you want to know, it's called the oxalate ion. Okay, so I'm going to let you finish that one up on your own. And we're going to move on to write a balanced equation for the ionization of perchloric acid in water. So now we're talking about acids and bases. So here's perchloric acid. Well, here's chlorate. That's chlorate ion. And this is nitrate ion. And this is perchlorate. So you'll notice for me to get to the perchlorate, I actually started with chlorate. I remember the 8s and then I go from there. The perchlorate has one more oxygen. So the nitrate ion makes nitric acid, and the formula is HNO3. Since the charge is -1, I add 1 hydrogen. So if I have perchlorate ion and I want perchloric acid, what am I going to do to this with a -1 charge?
Just put an H on.
Add 1 hydrogen, and there's perchloric acid. So we're supposed to write the balanced equation for the ionization of perchloric acid in water. I'm going to show you how to do it 2 ways. Now, I'm going to be honest with you and tell you I don't know the state of this when it's pure. So here, if you put it into water and it ionizes, you should get H plus, aqueous, and ClO4 negative. Now, this is one of the ones where I told you did not need to know whether it's strong or weak. So you don't know whether to make this a single arrow or 2 arrows, okay? So don't worry about that. It's a strong acid, so it should have a single arrow. So this is one way to write it out. So here, if this is a solid, it dissolves and comes apart. If it's a liquid, it dissolves and comes apart. If it's a gas, it comes apart. I don't know what the state is there, but in its pure state, all of these atoms would be bonded together. Another way to do it is this way. And I'm going to put a question mark here. And I'm going to put H2O. And H2O at room temperature is a liquid. And what happens here is this H plus actually adds to H2O. So this is an H plus bonded to H2O. This is like a molecule, except it's got a charge. And what is left is the ClO4 negative, which is aqueous. So this is called the hydronium ion. And when you look at it this way, you can see that this guy has given away a proton, right? Here's what it became. So it's given away a proton. Another way to say it is it's a proton donor. And proton donors are Bronsted-Lowry acids. Here, the H2O, you can see when it becomes this, it accepts a proton. So Bronsted-Lowry bases are proton acceptors. So this is a great way to show you have a proton donor and a proton acceptor. And so this is actually your acid, and this is your base. Water is a base. It's not a very good base. Water can also be an acid. It's not very good acid. Okay, so these are 2 ways of showing the ionization of perchloric acid in water.
Hey, Tony,
Yes,
is the top one the Arrhenius one?
that would be more the Arrhenius, because the Arrhenius definition is it produces H plus in water. How do we know this is in water?
Aqueous?
Aqueous. So what's BL stand for?
Bronsted-Lowry?
Bronsted-Lowry, because you know I'm not going to write that out. You guys are lucky I wrote Arrhenius. And I'm practicing to be a doctor. I'm going to quit this job here and go to med school. So I'm going to start writing it like that. You think I'm ready to be a doctor, maybe? Pretty close, huh? Probably that's too easy to read. So maybe more like, I think that's the ticket. Arrhenius. Okay. So do we understand there are two ways to do this correctly? Okay. So let's keep going. Phosphoric acid can supply 1, 2, or 3 H3O pluses in aqueous solution. Write balanced equations to show this successive loss of hydrogen atoms. I'm going to use the Arrhenius way because it's quicker, okay? And here I'm actually going to do this. I'm going to put AQ here. So here I'm showing how it supplies. Oh, actually it says H3O pluses. Can't do this. If I want to show H3O plus, I have to show it reacting with water. Darn it. That's a lot of writing. Now I know that this is a weak acid. That's why I have 2 arrows here, okay? So I like to write my H3O plus first. And what's going to remain is, well, since I have 1 extra hydrogen here, I have to have 1 less over here. And since these 2 are neutral, these 2 have to add up to being neutral. So that's got to be a -1. So there's 1. And this is an acid. And it can react with water. And it can do the same thing. Except you're not going to get H2PO4, you're going to get HPO4 2 minus. And then it can do it a 3rd time. So here's 1, 2, and a 3rd time. So what does this mean when we have these 2 arrows? That means when you put this guy into water, most of them stay together. Some of them do this. So in water, you actually have all 3 things, all 3 things. However, when this is in water, it can do this. So that means you also have some of this. I'm not going to write this again because I already have it there. And I'm not trying to represent these in proportions. I'm just trying to show you what's in water. And this can come apart, and that means you also have some of this. And so you might have, let's say we have 1 billion of these. You might have, let's see, you might have 1,000 of these. Let me think about that. Let's say you have 1 trillion of these. You might have 1 million of these. You might have 10 of these, and you might have essentially 0 of these. And here you're going to have about 1 million of these. Because here, when you look at how many of these are made, it's going to be equal to how many of those you have, how many of those, and how many of those. When you have these not all numbers all up together, it's like 1,000,000. Okay, so this is what you have in water. When you have this weak acid, you have all these things in water. Okay, so that would be the answer to that question. Write a balanced reaction for the reaction of sulfur trioxide gas with water. So this is something they talk about in the book. They talk about metal oxides and water. And they talk about non-metal oxides in water. So if we look at non-metal or metal oxides in water, non-metal oxides in water form a base. So for example, a metal oxide would be magnesium oxide, and it's a solid. And when you react it with water, you can actually get magnesium hydroxide. And this is one of those things where if you look at the solubility rules for magnesium oxide, there is nothing governing magnesium. And our book tells you oxides are not soluble. So this stuff is not soluble in water. But you may not know this. The definition of soluble means 10 grams will dissolve in a liter of water. If 9 grams dissolves, it's not soluble, but clearly something dissolved. So this stuff is considered to be not soluble, but a little bit of it can dissolve, react, and make this, which is also a solid. So this is one of those equilibrium reactions. And this is one of those equilibrium reactions where it is reactant favored. At least at first. And that's because this is not very soluble. So this is a base because it has hydroxide. And if you take a look, we're balanced, 1 magnesium, 2 hydrogens, 2 hydrogens, 2 oxygens, 1, 2, and 2 here. So you want to memorize that metal oxides and water create a base. Non-metal oxides and water do the opposite. They don't make a base. What do they make?
An acid.
An acid. So this is an example of that. So I'm going to put my non-metal oxide, sulfur trioxide, plus water. And basically you just combine all of this stuff to get your acid. So 2 hydrogens, 1 sulfur, 4 oxygens. So this is going to be an aqueous acid. This is soluble. And this is sulfuric acid. So if you can imagine, if you're burning coal, coal is made from, it's produced from, plants that have been dead for millions of years. And plants are made out of living tissue, which means it has carbon in it, phosphorus, sulfur, all sorts of nonmetals in there, as well as some nonmetals. So when you burn coal, you're actually going to be burning some sulfur. And so you'll get sulfur trioxide. When you burn all these nonmetals, you end up with oxides of the metals. So when you burn the nonmetals, you end up with oxides of the nonmetals. You also end up with oxides of the metals that are in there. For instance, if you burn coal, there is some sodium in there, so you'll end up with some sodium oxide. Now, the interesting thing is that this is a gas, but when you burn metals, you get solids. So the ash is basically metal oxides, because the non-metal oxides are gases, they float away. So if you're burning coal and this floats off into the atmosphere and it rains on this, you get acid rain. And this was a big problem in the previous century, the 1900s, not the 20,000s. So this acid rain was reacting with limestone and the such, and it was dissolving statues and things like that. So what do they do to prevent this from happening? Well, they said, well, you know what? Instead of letting it react with rain, we're going to react it with water before it ever gets out, turn that into acid, and then we're going to sell it. So you prevent acid rain while simultaneously getting a product you can sell. That's business. Okay. It's good for the environment and it's good for business. It's a win-win. That's one of your true win-wins, I think. So you want to remember these two. Now, there are some other examples, so I'm going to give you one now. So what product do you make from CO2? Because you also get this from burning coal. So H2O. H2CO3, right? What kind of acid is that? It's called carbonic acid. Now, this is a weak acid and this is a strong acid. So carbonic acid doesn't really cause that acid rain type of stuff because it's a weak acid. Now, if CO2 made a strong acid, I guarantee you that all the governments of the world would do a lot more work to try and get rid of CO2 gas getting into the atmosphere. Okay, so that's that one. Any questions on that last one? Okay, let's take a look here at complete and balancing the following. So the deal with acid-base reactions is they all kind of follow this for the net ionic. This is not the net ionic for an acid-base reaction, but it is the net ionic for a strong acid and a strong base. So the thing you're supposed to notice here is that you need one of these to react with one of these and you get one of these.
Mhm.
So when you're trying to balance these things, you want to make sure that the proportions of these two are the same. So if you have two H pluses, you want two OHs. If you have three H pluses, you want three OHs. If you have four OHs, you want four H pluses. How do we change the number of hydrogens in a compound? Are we allowed to change the formula?
Just put
No,
K.
just the coefficient. So let's take a look at A. How many hydrogens do you see?
3 in the,
3. And how many OHs do you see?
this one.
So this is not a match made in heaven. I want 3 of these. So to do that, I'm going to write 3 KOHs. Now, if I have 3 of these and 3 of these, how many waters am I going to make?
3.
3. And let's take a look at what remains here. Have I used the 3 potassiums? Nope. So that's part of my product. I'm going to automatically put that as a subscript. Have I used my phosphate? Nope. Solid, liquid, gas, or aqueous?
Aqueous.
Aqueous because of the potassium. And there's your balanced reaction. Boom. So what were the steps here? Step 1, find your acid, find your base. Step 2, count hydrogens, H pluses, count OH minuses. Step 3, change the coefficients so that you have the same amount of H pluses and OH minuses. Step 4, that's how many waters you get. Step 5, the rest of the ions form the salt. Okay, so give this one a shot, see what you can come up with. I really got to get that Jeopardy theme music on my computer somewhere. When you're done, give me a little, I'm done.
I'm done.
Oops, sorry. So how many hydrogens here?
2,
2. How many hydroxides?
2,
2. So we don't need to change any coefficients. How many water are we going to have?
2.
2. I'm going to put my AQ there. We have a calcium left over, and we have a oxalate left over. Now, it turns out that oxalates are not soluble. How would we know that this is not going to be soluble?
Well, calcium is not an alkali.
Well, actually, I think the answer is that if you remember which ones are soluble, the rest are not soluble. So this doesn't fit any of the soluble lists. So I would assume it's a solid. Because it's hard to memorize the ones that are not soluble. But this is one of the ones our book tells you, hey, those aren't soluble unless. Okay. Are we good? Okay, gone. Write a balanced reaction for aluminum hydroxide and sulfuric acid. So aluminum hydroxide, remember aluminum is a +3, hydroxide is a -1. So what's the correct formula? AlOH3, and we have to have parentheses because there's 3 hydroxides. Sulfuric acid, you start with the sulfate ion and you add 2 hydrogens. Okay. Now here I've written the base first and the acid second, but we can still handle that. This would be a solid because hydroxides are not soluble. Three hydroxides, 2 hydrogens. One's odd, one's even. So we probably want to multiply them together and get 6. So I'm going to put a 2 here so that we have 6 hydroxides. A 3 here so that we have 6 hydrogens. And therefore, when we have 6 H pluses and 6 OH minuses, how many water do we make?
6.
6. And what's left over here and here? Well, we're going to deal with the cation first. There's 2 aluminums left over. And there's 3 sulfates. And will this be aqueous or not? In general, sulfates are soluble unless you combine them with something like barium or strontium or one of those, or lead-2. So that should be soluble. Any questions about 38? Or are we good to go? I'm going to change that question. Are we good to go?
Yeah.
Yeah.
Okay. 164, refer to the book because it's too long to write. So we're going to skip that. Write 2 chemical reactions, one in which H2PO4 is a Bronsted acid, and the second in which this is a Bronsted base. So they tell us what it's going to react with. So here, H2PO4 minus, and this is going to be aqueous, and the carbonate is going to be aqueous. And this is a weak acid, so it'll probably do something like that. Now they want this to be a Bronsted-Lowry acid. So a Bl acid, which means it has to donate a proton. So donate a proton means the same thing as lose a proton. So I'm going to write that way over here, HPO4. When you lose a proton, you're losing some positive charge. And if you lose positivity, what happens to your attitude? You become negative. So if I'm losing an H plus, this has to become more negative. So that's a 2 minus. So do you follow how we got from here to here?
Yes.
Yeah.
Okay. Now, this is going to be your base. So this is a blib, a Bronsted-Lowry base. It accepts a proton. So we want to write this with a proton. So here, HCO3. And if this is -2 and this is +1, they add together and make a -1. And so here is this acid acting, this is this guy acting as an acid with carbonate ion. Okay, let's take a look at the next one. The second, in which HPO4 2 minus is a Bronsted base. So HPO4, and I'm going to leave the state off of it for right now. These are all going to be aqueous, but I'm going to leave that off for right now, just for brevity. So this is a BLB, which means it accepts a proton, right? And we're going to react it with this CH3CO2H, which is a Bronsted-Lowry acid, which donates a proton. You know, sometimes when we write donates, I almost wish that they had used the word loses a proton or something like that. So with that previous reaction, I'm not sure if I wrote the double-headed arrows, but this is also going to have the double-headed arrows. So if this guy accepts a proton, I'm going to draw it over here. What's it going to look like? Well, 2 hydrogens, 1 phosphorus, 4 oxygens. And if it gets an H plus and it's already a 2 minus, you have to add those together and you get a -1. So what happens when this donates a proton? You have to lose a hydrogen, and it's this one. So we're going to write CH3CO2, and whatever it makes, when it combines with H plus, it has to give us the original Bronsted-Lowry acid. So that would be this. Another way to figure this charge out is, do you see on the left how this is -2 and this is 0? And this is -1. So this has to have a charge so that it adds up to -2. So that's another way to get that charge. This is the acetate ion. Now, you might be wondering, you know, why does he draw these little arrows here? Because these are actually called conjugate pairs. And conjugate pairs differ by an H plus. And for these conjugate pairs,
Right?
one of them is an acid and one's a base. This is actually a Bronsted-Lowry acid. And this is a Bronsted-Lowry base. So for the pairs, how do you tell which is which? The one with more hydrogens is the acid. Okay, so that's how you do this. And did you see in this particular reaction, did we need water at all? And the answer is no. All right, let's take a look at another one of these. I'm sorry, did I go too fast? We okay?
Yeah.
Okay, let's move on then. Balance the following equations. Now, in this case, it looks to me like it's a mishmash of things that we've been learning. Like B, wouldn't we agree that B is an acid-base reaction?
Yeah,
How do I know?
because you see OH and H.
Yeah, I got a base and I've got an acid. If we look at C, doesn't this look like a gas forming reaction?
Yes. With the
Doesn't
CO2
D
model.
look like a precipitation reaction?
Yeah.
Two ionic compounds make a solid ionic compound. So what must A be? It's that type of reaction we haven't looked at yet, which is called redox. How do you recognize a redox reaction? Well, not all redox reactions are like this, but most of them are. And when I say like this, I mean this. Pure element on one side, or pure element in the reaction somewhere. If you have a pure element in the reaction, it's most likely a redox. Now, you'll notice I didn't say pure ion, I said pure element. So if we had zinc plus 2, that wouldn't say redox. Pure neutral element in the reaction, it's going to be a redox. So what type is A?
Redox.
Redox, because of the zinc, also because of the H2, pure neutral element. Okay, so we'll only do one of these because we already know how to do the net ionic. One zinc, one hydrogen, two hydrogens. So we're going to put a 2 there. And now we have 2 chlorines and 2 chlorides. So what do we bring down automatically?
The gas and the
The
solid.
gas
And the solid.
and the solid. They're automatically in the net ionic. Now, for this, we need to realize that it's H plus and Cl minus, right?
Right.
And they're both aqueous. Over here, it's zinc 2 plus and Cl minus, and they're both aqueous. And there's 2 of these and 2 of these. So these guys, bonk, don't belong in the net. But these 2 H pluses, they do. Because these are different than that. And the zinc, it belongs. And so there's your net ionic. Let's just talk briefly about how we would balance the second one. Wouldn't we count H's and count OH minuses?
Yes.
How about C? How would we balance that? And the answer is, you see that CO3?
Yes.
Our job is to turn that into H2CO3 because H2CO3 makes these two things. So that needs to become H2CO3. How many hydrogens do you see over here? 1. We need 2. So what do you have to do to that guy?
The 2 in front.
Put a 2 in front, and then it'll all work out. Here, 2 ammonium ions, 1 ammonium ion. What do you have to do? Put a 2 here, and there you go. Okay? So we're going to move on from that. 46, refer to the book. Write balanced net ionic for the following: the reaction of aqueous solutions of silver nitrate and sodium iodide. So this is really a precipitation type of problem, or precipitation reactions. So for precipitation reactions, hopefully you've read through the rules and you kind of know what's going on. So here for A, aqueous silver nitrate, we memorized silver as Ag plus. Nitrate we know is NO3 negative. And so you can see I'm going right away to the ions. And sodium iodide is this. And when I'm trying to figure out the precipitate, what do? We say, well, this guy's always soluble and this guy's always soluble, so it's not part of the precipitate. So that means it must be these two, which is AgI. And these two, what happens to this nitrate? Nothing. What happens to the sodium? Nothing. So if this is my overall ionic reaction, what's the net? Well, I get rid of that because it hasn't changed. I get rid of that because, whoops, excuse me, that because it hasn't changed. And I include these things in my net. So you're going to do the same thing for B. Now, why do you think I gravitated towards this being a precipitation reaction instead of, say, a redox? And I'll tell you the answer. If you look at this, I don't see any evidence of a pure neutral element. So I don't think it's a redox. Why do I think it's not an acid base? I don't see the names of any acids or bases in here. Why do I think it's not a gas forming reaction? Well, I know gas forming reactions happen when you have a carbonate in there, also sulfites and things like that. And I don't see those. So that's why I was thinking, oh, this is probably a precipitation reaction. Now, do you see how this one might give me pause and think, oh, this could be a gas forming reaction because it has carbonate. And I know carbonates do that. But what would pull me back away from a gas forming reaction? And the answer is, I know that the carbonate has to react with an acid to be a gas forming reaction, and that's not an acid. Okay, I'm going to let you do B on your own. Okay, so here we have a carbonate with an acid. This is a gas forming. We're going to skip this one. This one, we have a sulfite with an acid. This is going to be a gas forming. I'm going to let you take a look at that in your book. And I wanted to start just a little bit of oxidation reactions. So you'll notice they're asking about the oxidation number. And I'm going to show you why. So this is a redox reaction. Redox reactions involve the movement of electrons. And in your lab, I give you an example of a redox reaction where you take silver nitrate, aqueous, and react it with copper metal, and you make copper 2 nitrate, aqueous, and silver metal. So this is a redox reaction. If we write the net looks like this. And I should have a 2 here and a 2 here. So you can see that for the net, I brought down both solids. Here, the nitrate ion is always soluble. The nitrate ion is always soluble. It doesn't change, so it doesn't belong in the net. So this is the net. And the net actually, in this case, has 2 half reactions. One reaction focuses on silver and the other focuses on copper. Okay, so this is 1/2 reaction, but there's something wrong with it. I do have 2 silvers and 2 silvers, but over here, each of these is a +1 charge. Over here, each one of these has no charge. You can't have reactions where the charges don't equal on both sides of the equation. Not only do the number of atoms have to be the same, but so do the number of electrons. And here we don't have the same number of electrons. So we need to add electrons to this to make it work out. So are we going to add electrons to the left or to the right? Well, electrons have a negative charge, so I'm going to add 2 electrons to the right. So this will be a -2 charge. This is a +2 charge. Add them together and you get 0. So this is actually 1/2 reaction. Let's look at the other half reaction. Can you see that we have a neutral atom turning into a cation? Where do we add electrons to this to make it work? To the left or to the right?
To the right.
To the right, because that way this will end up being neutral like that. Now, that's the way you figure out where to put the electrons. Now, how do we describe these situations? We say that silver 2+ is gaining 2 electrons. Well, I should say silver plus is gaining an electron, because really we have 2, 2, 2. It could be 1, 1, 1, right? So your silver ion is gaining an electron to become silver. What do we say about this? We say copper is losing 2 electrons to become Cu2+. And this is the part that confuses a lot of students because they see the word lose and you think you're supposed to have a negative. And here that's a positive. But remember, we're talking about this guy right here. When this guy becomes this, what happens to him? He doesn't gain 2 electrons, he has to lose 2. Or you could be more benevolent and say he gives away 2 electrons. And the interesting thing is, where do you think these 2 electrons go? Well, where do you think the silver ions are getting their electrons from? From this copper. So if we look at what's really happening in this case, is this. Here's my copper wire, and here's a copper atom. And here's another silver ion, and these are floating around in water. They're soluble because they're with nitrate. These guys bump into the copper, and what happens is when they bump into the copper gives 1 electron to this silver, gives 1 electron to this silver, and that copper now floats away with a +2 charge. And the reason it has a +2 charge is because this is the copper floating away. The reason it gets a +2 charge is because it just gave away 2 electrons. So what happens to this silver ion, which is soluble in water? Well, I'm going to tell you. It becomes neutral and it's no longer floating in water because it's a metal. Metals don't dissolve in water. So guess where these silver ions end up? They end up as silver atoms on the copper wire. And eventually the silver is going to be all over that copper wire and you won't even see the copper wire anymore. And eventually the copper wire will eventually just dissolve into these copper ions. So this is a redox. And you'll notice in this redox reaction, do you see a pure element? Yup. Do you see a pure element? Yup. So that's why pure elements are a giveaway for redox reactions, because if it's a pure element, it has 0 charge. And if it's in a compound, it'll have some sort of charge. So that means that electrons are being exchanged. So how do we figure out what's going on? I'm going to write the two half reactions again. Silver ion is gaining an electron and becoming silver atom. And we have copper turning into copper 2 plus. And here we say that the copper is losing electrons. So you got to somehow come to terms that lose simply means the electrons are a product. So you want to remember the following terms to help you understand what's going on. If you gain electrons, what this means is that you're reduced, or we say that's a reduction. And you're the oxidizing agent. If you lose electrons, you're oxidized, or that's oxidation, and you're the reducing agent. And a good way to remember this are two terms. So I'm going to start with this one. Oxidation is losing electrons. Oxidation is losing electrons. Reduction is gaining electrons. Reduction is gaining electrons. And you put these two words together and you get oil rig. Like those things that you find in the Gulf of Mexico where they're drilling for oil. You got an oil rig. Whole nother meaning in Humboldt County, but we're going to go with the Gulf of Mexico meaning. Is that clear?
Yeah.
Because we're a good class. So oil rig. So you want to kind of remember that. That helps you. Some people do something else. They go Leo, loss of electrons is oxidation, and Ger, gain of electrons is reduction. And so Leo, we know, is another name for a lion, right? Lion. Leo is another name for a lion. And what sound do lions make? Grrr. Leo goes grrr. I like oil rig better. Okay. So what happens if you can't see ions in this? For instance, why do I know that's a redox?
Pure element.
Pure elements. I don't really see how this is losing or gaining electrons because it's neutral and this is a molecule. So each of these atoms technically is neutral in a molecule. So I can't tell what's going on. So someone invented oxidation numbers so we could figure out what's going on. So there are rules to oxidation numbers. I'm going to show you how to assign oxidation numbers, and I'll talk about the rules as we go along. I'm not going to write down the rules. That's something you want to do for yourself so that you understand them. So for A, fluorines are going to be a -1 each. And this phosphorus is going to be a +5. And the reason for that one, two, three, four, five. I need 6. If you add up the oxidation number on each of these elements, it should equal -1 because that's the charge. So the fluorines are going to be -1 in this case. You add those all up and you get P minus 6 is -1. and then P is equal to positive 5. So you should have learned two things here. One, or two things, maybe three. I assigned fluorine first and then phosphorus. There's a reason for that. And that if you add up the oxidation number on each element, it should equal the charge. So one of the rules you need to learn is that if you have fluorine in a compound, not a pure element, but in a compound, its oxidation number is -1. Okay, let's look at B. H2, ASO4 negative. Now here's how I'm going to do this one. I'm going to assign the oxidation number to hydrogen first. It's a +1 in compounds, in most compounds. The oxygens are -2 in most compounds. And arsenic we have to figure out. So when we add up all these oxidation numbers, what should it equal?
-1.
-1. So now we have 2 plus arsenic -8 is -1. Arsenic -6 is -1. And then arsenic must be +5, I think. So here, these are +1 each, +5 and -2 each. And you'll notice when I put the oxidation numbers here, I don't put the total. I just put down the oxidation number on each atom, just like I did up here. That's important. Don't put the total. Don't do this. +2, +5, -10. Don't do that. It doesn't help you. Put down the oxidation number on each atom. Okay, so that's B. C, we're going to assign the oxidation number for oxygen. It's a -2. So what does uranium have to be?
+4.
+4. Because these two numbers have to add up to be 2+. How about N2O5? We're going to do the oxygens first. They're -2 each. What do the nitrogens have to be?
+5.
+5 each. Okay, so now we're in a place where we can start talking about rules now that we've applied some. First rule is that if you add all of the oxidation numbers in a formula, it equals the charge. So if the charge is 0 on the formula, it equals 0. If the formula is an ion, it's the charge of the ion. And there's really a pre-rule for one. The pre-rule would be every atom gets an oxidation number. Every atom gets an oxidation number. Okay, the second rule would be atoms in pure neutral elements have an oxidation number equal to 0. We didn't see any examples like that. But if you had this, that would be a 0. If you had this, that would be a 0 for each one. 3, the oxidation number equals the charge in monoatomic ions. So if you have an Na+, the oxidation number is +1. If you have an O2 minus, the oxidation number is -2. 4, in compounds, the oxidation number of fluorine is -1, hydrogen is +1, oxygen is -2, and chlorine is -1 in this order. So these are your basic rules. So let's assign some oxidation numbers that are not here. Some more interesting ones, if you will. Like this one. What are the oxidation numbers?
+1. for
And the
hydrogen.
answer is they are +1 and -1, which seems to fly in the face of this down here, doesn't it?
Yeah.
But let's look at the rules. If you add up the oxidation number in a formula, it equals the charge. What's the charge on this sucker? 0. Okay. Atoms in pure neutral elements are 0, none there. The oxidation number equals the charge in monoatomic ions. Oh, shoot. This is a metal. This is a non-metal. What does that mean about this compound?
A monoatomic ion.
It's ionic. And if it's ionic, what comes first, the cation or the anion?
Cation.
So this is an Na plus and an H minus. So what is the oxidation number of this guy? +1, this guy, -1, the charge on the ion. We don't even get to rule 4. Let's take a look at another one. H2O2. No pure elements, no ions. What do we assign first, hydrogen or oxygen?
Hydrogen.
So these are +1 each. What are the oxygens?
-2 each.
Well, let's take a look here. That's a good first guess. That adds up to -2, right?
Mm.
That doesn't have a charge.
-1.
-1 each. What about this one? OF2. None of this applies except for number 4. Who do we assign first?
Chlorine.
So that's -1 each. What's the oxygen have to be?
-2.
+2.
Yeah.
Okay, so, once we do this, we can't just move on down because we still have to know that they all have to equal the charge. That's the first rule.
Mm.
So if this is a -1, we can't make that a -2 because it won't sum to the charge. So these are some tricky ones that I'm trying to point out to you that they don't really show over here. Yeah.
Tony, so we should take all of these rules and do them in order, and also for number 4, those ones are in order too.
Yep.
Okay.
So it's a FHOCl, which sounds like a bad word, so I'm not going to say it. I'll just say it's like FOH. And you can imagine the rest, okay? So, or you can think of another way. Friendly hospitals, that's not going to work. French,
Often carry lice.
what's that?
Often carry lice.
Do they?
I don't know.
I'm not going to go to a hospital then. My goodness, I don't want lice. Have you ever had? If your kids ever get lice, you're going to hate it. And If your kids go to public school, it's probably going to happen.
Head lice sucks.
I know, especially when your son has hair down to the middle of the back of his back.
I have 3 daughters, and all 3 of, well, my oldest now has short hair, but at one point we all had long hair. And we never really had a problem until we moved into the apartments we're in now. But last winter, we had a really bad problem around the apartments. And so they all go to school together. And so it was at the school, and then it was here, and it took months for it to go away. It was bad.
Yeah, you gotta
We're
wash.
now in the habit of checking every day.
You gotta wash all the bedding. Use that little lice comb.
Oh, yeah.
Let's do one last problem, and then I'm gonna let you go. Which of the following are redox reactions?
2 or B? B is a redox
Why do you say B is a redox?
because of O2.
Do you see how I asked the question that makes you question yourself?
Yeah.
And you're supposed to say, not because it has O2. You're supposed to say, well, Tony, you said that if it's got a pure element, it's a redox. It's got a pure element. And you got to have attitude. My kids have attitude because I treat them like this all the time. So why do you say B's a redox?
That was just the first thing that came to my mind.
No, that's not enough attitude.
Okay. Well, B's a redox because it has a pure element.
There you go. Any other redoxes here?
Maybe C. Oh no, C.
Maybe C. Maybe C. How about C because it's got a pure element? Because
C.
if we assign redox numbers, what's the oxidation number on this oxygen? Pure element. 0. What's the oxidation number on this hydrogen? -1. This oxygen will be, or +1. This oxygen will be a -2. And when the oxidation number changes, that means it's a redox. 0 to 2, it's a redox. Okay? We will do some of these redox ones next week on Monday. And we're also going to be doing these things called titrations. That's going to be your next lab on Tuesday. We're going to do a titration of vinegar. So you need to buy some vinegar. White vinegar is fine. You want to buy the cheapest you can buy. And you'll definitely need goggles for next time. Definitely. Okay, thanks for tuning in. I appreciate it. I hope you all have a good weekend. And
Thank you.
if one of you is in control of the weather, could you please bring the sun out?
I wish. That'd be really nice. I could send all my kids outside.
Yeah, well, I would do it anyways. All right, thank you for attending, everyone. Bye-bye.
Thank you. Have a good weekend.